Hello, everyone. Thank you for joining our webinar, Debunking the Mystery of Air, Water, Gas, and Ice in Food Manufacturing. This webinar is hosted by Ruby Ochoa of Trace Analytics and William Lips of Eurofins Analytical. I'm Genevieve Randall, and I'll be moderating this webinar. Before we begin, I'll let you know more about how this webinar will run. The webinar is being recorded, and the slides and recording will be available for you within 3 business days. A short Q&A session will follow the presentation to answer viewer-submitted questions. During the webinar, you can submit questions you have using the webinar sidebar menu. Select the Questions tab, type in your question, then hit the Enter key on your keyboard. Remember, you can submit questions throughout the webinar. Now I'll give a quick overview of Eurofins. Eurofins is driven by our mission to contribute to global health by offering the highest quality testing, training, auditing, and consulting services. We strive to listen to our customers and not simply meet, but exceed their expectations. Our footprint is global, with 45,000 staff in over 800 laboratories across 47 countries and a portfolio of over 200,000 analytical methods. Eurofins provides a unique range of analytical testing services to the pharmaceutical, food, environmental, and consumer product industries and to governments. Ruby, now you can go ahead with your presentation.
Okay, thank you very much, Genevieve. I work with a great group of people at Trace Analytics. We've been in business, we're celebrating our 30th year in business. A much smaller laboratory than Eurofins, but we have a really good group of people that are dedicated to one thing, and that is testing compressed air and gases. So I will be talking a little bit about GFSI, a few of the schemes under GFSI, ISO 8573, the purity limits that they've established, a little bit about the contaminants, as well as creating a risk assessment and a monitoring plan.
Okay, before Ruby continues her presentation, we're going to pause for a quick polling question. Question should now be on your screen. And it is, are you currently testing your compressed air? Select your answer. I'll leave the poll open for about 30 seconds, and then I'll close and share the anonymous results. Okay, I'm going to close the poll now. And it looks like the results are about 50-50, with just over 50% saying that they don't currently test their air. Okay, now Ruby, you can continue with your presentation. Thank you.
Okay, great. So the Global Food Safety Initiative has benchmarking standards for certification programs like SQF, BRC, Primus, GFS, and the standard basically states that that they require that the quality of compressed air, water, in any form that comes into direct contact with either food or food packaging shall present no risk to product safety. So let's talk a little bit about what some of these schemes state. They take that information from GFSI and create the requirements when they come do an audit at a food facility. So SQF in the Edition 8 states that compressed air and other gases like nitrogen or carbon dioxide that come into contact with food or food contact surfaces shall be clean and present no risk to the food. It also states that the compressed air systems, which would include distribution piping, any systems used to store or dispense these gases throughout the manufacturing process, shall be maintained and regularly monitored for quality. Pretty simple statements. As far as water, they also state that it should meet your local, national, and recognizable potable standards, water standards, and that any samples that are taken shall be taken within the facility, and that the frequency shall be risk-based and at a minimum annually. I'm throwing in some information about water. I won't be talking about water, that's William's area, but just thought we'd go ahead and cover it here at the very beginning. SQF is one of the most common schemes that we see based from our customers. And they also have some useful information to back it up as far as they have frequently asked questions. We have some links at the very end of the presentation where you can go to the source document and download it. The next one is Primus GFS, and this particular module puts them in sort of a question and expectations format. They state that compressed air or other gases that are that have direct contact with the product, food contact areas, or inside the surfaces of packages shall be free of contamination. When did that change? Okay. And that it shall meet your program requirements, that your testing should be based on a risk assessment. They also state that a preventative maintenance program will certainly help prevent contamination of products. The British Retail Consortium states that all water, including ice and steam, should pose no risk of contamination, and that it should be at least analyzed annually. They also state about air and other gases that if used as an ingredient or in direct contact with products shall be monitored, and it should not represent a contamination risk. They also state that it should be compressed air should be filtered at the point of use. So what do all of these things have in common? Basically, they don't give you an answer that we frequently get, and that is, well, what should the quality be? They don't give you those exact limits, and they all pretty much point to you need to do a risk assessment to figure that out for yourself. And really the reason for that is there's such a wide variety of products out there and uses that it would probably not be a good idea if they said this is what it must be. I'm having a little difficulty. These slides aren't popping through very well. Okay, so let's talk about contaminants in compressed air. What are they? Particles, water, oil, microorganisms. These are all contaminants that ISO 8573 and the Compressed Air and Gas Institute have stated are the primary contaminants you're going to find in the type of air that's used in manufacturing. So, excuse me, where do they come from? There's a variety of sources. It starts at the intake of the compressor. There are millions of both viable and non-viable particles out in the ambient air. There's water present in ambient air. Some places much more humid than others, but the compressor is designed to remove that, right? Oils are present from the exhaust of cars, trucks. There's, you know, you name it, the contaminants are going to be in the air that goes into the compressor. So the compressor can also be a source of some contaminants. Certainly there's going to be some oil carryover. There's going to be wear particles, and these are just from normal operation. And the oil carryover obviously is from an oil lubricated compressor. If it's not oil lubricated, then that is eliminated. But you do still have hydrocarbons coming in through the intake, right? So you still have to filter for that. Another source of contamination is your distribution piping and your storage receivers. Distribution piping, we see a wide range of the different types that are out there. We have some customers with facilities that are 30, 40, 50 years old, and they've got black iron pipe throughout their facility. That doesn't mean that they can't produce good, clean air. It just means that there are some additional risks there, especially if you have a refrigerated dryer. You take a refrigerated dryer which has moist air and you put it with a type of pipe that rusts, and guess what? You're going to have particles flowing down the line, and that's when it's really important to add additional controls like point of use filters to remove those contaminants. Storage receivers are typically also made out of black iron, and they will rust as well. The other area that is frequently overlooked are point of use items, and by that I mean you've got a great system, you've got your compressor, you've got point of use filtration, everything according to specs is going to give you some good clean air. And then you add this 20-foot hose made out of rubber with a nozzle that's got some brass parts in there, some O-rings in there, and guess what? You've now added contamination after your point of use filter. So we frequently advise customers to take a sample the same way you use your air, so that we can catch those types of problems. So sources of contamination are from a variety of sources, and let's move on to see why these are important to you. You don't want any of these types of contaminants affecting your quality for your food that you're manufacturing. Obviously, that's the biggest goal. The other is just the physical appearance of contamination. You don't want an oily residue on the package that you're shipping out, right? The other requirement for clean air is the performance of your equipment. Opening and closing of valves don't do well if there's oily residue, or if there is large particles that will affect the proper operation. There's lasers that are being used for sorting and a variety of other functions that must have clean, dry air. And obviously, the primary reason test is to prevent things like recalls and microbial growth in your process. So 8573 is from ISO, and they have, ISO 8573 has 9 different parts. The purity classes are located in the first part, -1. This is a chart that basically we put together combining all the different purity classes. On the left-hand side, you'll see classes from 0 down to X. Across is your particles, water, and oil. For different purity classes, you have different limits. And these at the very bottom, you don't ever want to be there. That's typically when you're seeing liquid oil, liquid water flowing from your outlet. So we primarily are looking at these purity classes for our customers. Water has 6 different purity classes. The top 3 basically are for desiccant dryers, and the bottom 3 are for those with refrigerated dryers. Oil is for class 1 and 2 requires two different types of analyses. One is oil aerosol and oil vapor. When you get to a class 3 or 4, the oil vapor is not required because the limits are a little bit higher. And certainly liquid oil is way down here. When you communicate what you want, understand that this is a common language that your compressor manufacturer, your filter manufacturer, and your analytical laboratory can understand. And the proper way to communicate that would be designating ISO 8573-1, the edition, which is 2010, and then in brackets, the purity classes, always in the order of particles, water, and oil. So that makes it easy to communicate what it is that you need. Here's a couple of examples. The first upper part of this is just a chart that we put together indicating for the highest risk product, you would more than likely want a class 1 or 2 for particles, desiccant dryer, that would be classes 1 to 3 for water, and then oil would be the lowest possible, either a class 1 or a class 2, and then it just moves on forward depending on your risk. These are examples from some of our customers, and they vary widely. We should probably update this to include some of the other classes that we see frequently requested. And so that basically, the reason we like 8573 so much is that it allows you to pick and choose the purity classes from, you don't have to just pick one and say, oh, I must need a class 1. You can make combinations, and that's what I wanted to show you here. There are, the British Compressed Air Society has put together a really good best practice guideline. It's a document that talks about compressed air in the food and beverage industry. They recommend, if you're using air for direct contact, that it should be a class 221. If it's indirect, it should be a 242, and you should do at least semi-annual testing or based on your risk assessment. What we recommend, if you don't have your purity limits already established, to do a baseline analysis. That's basically, you're going to take a test, we're going to analyze it and determine where you fit based on the ISO 8573 purity classes. Once you've gotten sufficient data from enough sampling points, do a trend analysis. Take a look at what these results are saying. Do you have an up and down? Is the quality varying throughout the year? You won't know that without actually looking at your data and plotting it out. We also recommend at least semi-annual testing so that you can gather that information. Once you have that information and you've got a few years of good solid data, then you can say, okay, I'm going to meet a class 221, and based on my analysis, I can do that based on, say, semi-annual testing or once a year. Whatever it is you decide, make that decision based off of information about your specific system. So, assessing your system for risk. Nobody wants to hear that they have to do a risk assessment first, but quite frankly, that's what you've got to do to determine what's at your facility and what product you're making, and make a determination of the quality that is absolutely necessary for you. So how do you go about doing that? The first thing is, what are the hazards? Well, we've told you already about particles, water, oil, microorganisms. Those are the potential hazards within a compressed air system. Assessing the risk. We've got, that topic could take at least an hour or more to discuss, and we do have some links at the end of the presentation on an article, a chart that you can download. But basically, what you need to do is go walking around your facility armed with your facility drawings so that you can identify all the points of use that are in direct contact or indirect contact with your product. Identify what type of materials are being used. Do you have those nozzles there? Do you have the rubber hoses? And what kind of piping? I'll show you the checklist. We've got a checklist on the next slide. Once you've done that, what are some of the existing controls that you've got? Do you have point of use filters, or do you need them? If additional are necessary, this is the point when you're figuring all of that out. And then I strongly recommend that you review your risk assessment. Schedule it, put it on your calendar, or put it on that checklist for annual review. Things change, new product lines come in, additional piping is added. When you break into a line, it certainly can create a lot of particles that are going to move down the stream just from the function of breaking in and adding piping. So review your plan to make sure that it's always current. This is the checklist I was talking about. This will really be helpful because part of your risk assessment is to document what you have. This will allow you to write down the type of compressor you've got, what kind of piping you have, the type of fittings that you've got installed. Did you use glues to put the piping together? Is it, block iron? All of this, once you've done it, you've got it. That's part of your documentation package. And then it's a much easier thing to review the following years. Setting up a monitoring plan. Excuse me. Any good monitoring plan, right, is going to be based on what? Risk assessment. What is your system capable of? In other words, do you have a refrigerated dryer, but you need one particular product line that absolutely has to have dryer air? That's where you would add additional point of use filtration. Second part of your monitoring plan would be to figure out what the quality needs to be. You can use ISO 8573 purity classes. We've got other customers that have custom specifications. And then the next step would be to figure out who's going to do the testing for you. Are you going to use a service distributor to come in and do that for you? Are you going to work directly with the laboratory? You need to be able to communicate what it is you need from them. And then establishing your sampling plan. So your sampling plan, you need to determine how many samples am I going to take. As you notice from the different requirements, it doesn't state that. That's going to be based on your risk assessment of what you have, how many points of use you've got at your facility. If you've got one, boy, you are a lucky person. You've got one sample that you can take, right? A lot of our customers have a large number of production lines and points of use. So they go with a percentage-based sampling plan. They might decide that in the long run, they would really like to see 100%, but they're going to break it up and do 20% a year or 25, and over a period of time, actually get all that information. Not too many of those customers, I will admit. But the other one that is really common or useful is one that's based on a maintenance schedule. And you would take samples. What we recommend is take those samples before you change the filters or change the oil to see your worst case scenario from your previous test. Is the maintenance schedule that you have in place, is it keeping the quality of the air at the correct level for you for that time period? And sometimes you'll find out that filters need to be changed a little bit more frequently, especially when your facility is grown and you've added either square footage, more miles of piping, whatever it is. So it's useful to take that sample before. What we call a minimal sampling plan would be to take a sample pretty close to where your compressor system filters are located. That tells you how good your air is, and then take a sample at the furthest point from that filtration at the end of the line. And then a couple in between, especially taking into consideration new versus old piping. Perhaps you've got more than one compressor, making sure that all those mid-range, mid-level points are represented in your sampling plan. And then there's, like I said, that single sample. We have some customers that they take one sample once a year, and that might, more than likely, will get them the check mark that they need for their audit. But it is not truly representative of what's going on at your facility. Oh, we have a polling question.
All right, so we're going to pause for another polling question. The question should be on your screen now, and it is, how frequently do you test your compressed air currently? Annual, semi-annual basis, quarterly, another frequency, or not applicable if you don't? You can select your answer now, and I will leave this open for about 30 seconds. Okay, so I'm going to close the poll and share the anonymous results. And it looks like those that are currently testing their compressed air are doing so on an annual basis. And now Ruby will address frequency in her next slide. Ruby, you can continue on.
Okay, so I mentioned earlier that we recommend at least semi-annually. And the reason being is that the environment changes throughout the year: spring, summer, winter, fall. Or is that fall, winter? Yes. So the quality of the air going into your intake can certainly vary. Also, in the wintertime, people do things differently than they do in the summer. Those bay doors may be wide open. And the other thing is that there is maintenance going on throughout the year that may be affecting the quality of your air. So I think it's useful information, at least initially for the first year or two, until you have sufficient data that tells you that, no, everything's working exactly the same all year round. Once you have that information, you can actually do a trend analysis and see what really is going on in your facility. We've got some customers that include in their spreadsheet every time that filters are changed or something is added. If they've had an event, say the dryer went out and they had to do some major maintenance, they will include that information so that when they have the results of their air testing, they can make an evaluation of the quality, whether it was affected or not by the event, things like that. It's much better than to just receive your report, look for that passing report and file it. There is use in actually looking at the numbers and call your lab and have them explain it to you if you're unsure what the report means. Hello, there we go. So, one thing I will say is that whatever lab you pick, make sure that they offer you the options that you need. One size does not fit all. We have some customers that call up a week and a half before the audit and they need something really fast. So we have an option like that. It's called a basic, as well as something that's in the mid-range for those perhaps that need to do a number of outlets and they need to economize. We've got others that want a full comprehensive test so that they can make a determination of what they need for the future. We do that for particles, water, and oil, as well as for microorganisms. And that really brings me to the end of my presentation. It was a pretty quick overview. Didn't really get it to go into the meat of a lot of this information, but if I could get to the last slide, Genevieve, could you help me there? There we go. Basically, we've got GFSI schemes that are out there requiring you to do some type of monitoring of your compressed air and any type of inert gas like nitrogen, carbon dioxide. I hope you've gotten a little bit of information on how to go about setting up a monitoring plan that will complement your product specifically. And if you have any questions whatsoever, please feel free to give us a call at Trace Analytics. We'll be happy to help. And that's it for me. It's all yours, William.
All right, thank you, Ruby. So these are the links that Ruby referred to during her presentation, and these will be available in a email coming to you by the end of the week that will also include a copy of the slides and recording of the webinar. Okay, now you may continue with your presentation. Thank you.
Okay, thank you. In this presentation, we'll cover the uses of water in food and food processing, sources of water or where the water might come from, touch a little bit on water treatment and why maybe that matters, and then briefly cover some of the guidelines and regulations regarding safe drinking water. The biggest use of water in food and food processing is in primary crop production, where it is used for irrigation purposes. Livestock or dairy farming also require large volumes of water. Why does this matter? Because eventually the water that ran over your field or that the cows stepped in is going to become a source of your drinking water. Clean seawater is not potable, but is permitted for use in processing operations such as washing whole fishery products and shellfish. The reuse of water through recycling is becoming a vital component of food processing as a means to conserve water, reduce costs, and provide security of water supplies. Recycled water can be used in food processing or as an ingredient, but should meet the same water quality standards as your drinking water. In some circumstances, non-potable water is used by the food industry. In these instances, the water and its piping should be clearly identified as non-drinking water and not connect or mix with the drinking water supply that is used directly in food production. The types of water used for agricultural water are very diverse. Legally, your only requirement for health and safety is to monitor for E. coli or bacteria. However, keep in mind that irrigation water runs off and may eventually find itself into the surface water. For this reason, engineering controls should be made to decrease nutrients such as nitrogen and phosphorus in your runoff. These can cause pollution problems downstream. The sodium absorption ratio is a measure of the amount of sodium to calcium and can be used as an indicator for the suitability of a water that's chosen for irrigation. A high sodium absorption ratio is very bad for the soil, but the SAR, sodium absorption ratio, is limited information. If you are collecting data for SAR, you may as well add the other cations and anions that make up the bulk of the ions in water. Not only will a balanced water analysis provide the assurance that your SAR result is correct, but will also provide information on salts such as chlorides and sulfates. As a side note, this presenter has seen at least one instance where selenium in water affected livestock and another instance where high sulfate in water actually decreased selenium in the brains of sheep, causing them to die. The point is that water quality varies based on geography, and you should keep that in mind. Chlorine and quaternary ammonium compounds are two common active ingredients used for food contact surface sanitation. Both are less effective in the presence of hard water, especially when targeting bacteria that may be dried onto surfaces. For example, the addition of just 1% milk has been shown to dramatically reduce the activity of quaternary ammonium solutions. In addition, take care to ensure that the cleaning agent used does not interfere with the sanitizers. For example, quaternary ammonium compounds may be inactivated by binding with anionic surfactant-based soap residues. The secondary limit for total dissolved solids is 500 parts per million. Even at this concentration, a residue of salt can eventually build up. This residue can become visible on surfaces and even clog nozzles, such as the ones shown in this photo. If water comes from a municipal supply, it will be pathogen-free. If it is groundwater or surface water supply, it may be non-potable and should be disinfected before use on any surfaces that will come in contact with food. Ice for human consumption or that may come in contact with food for human consumption should be pathogen-free. Again, public supply or municipal water is almost always free of bacteria. However, if you filter through activated carbon to remove residual chlorine, there is a chance for the growth of bacteria. In addition, the water quality can affect aesthetic qualities of the ice. Essentially, the higher the total dissolved solids, the softer and more cloudy the ice crystals will look. I personally grew up in a town where the TDS and other secondary parameters always exceeded the secondary limit. Ice in the domestic refrigerator ice makers was very cloudy and would smell. If you want people to eat or use ice made from high TDS water, you will need to purify the water by reverse osmosis or deionization. At minimum, you should ensure any water that may end up in a final product meets or exceeds EPA or World Health standards. This is usually, but not always, the case with a public supply. If you source your own water, such as from a private well, you should at minimum test it for all EPA-listed contaminants against the EPA primary and secondary contaminant levels. An advantage to a private well, particularly from a very large aquifer, is long-term consistency in mineral content. A disadvantage is you should test it for indicator compounds such as pH and conductivity. You should test it often to ensure no significant changes are occurring. In addition, a groundwater supply should be tested often to ensure that it is pathogen-free, or you should add a treatment system to make sure that you kill all potential bacteria. Municipal supplies can also vary, particularly in water-challenged areas, but also seasonally based on drought, snowmelt, rainfall, or other weather conditions. This variability in supply can cause a variability in the taste of a product. If water is a key ingredient, you may want to consider additional treatment so that what goes into your product is always the same. If you add treatment, we recommend analysis before and after the treatment to monitor the effectiveness and to detect issues before there is a problem. Most municipal supply water comes from surface water, with the remaining being groundwater. In the groundwater category, some of them are actually mixed ground and surface water. Since public supplies must comply with the Safe Drinking Water Act, you can assume that most supplies pass Safe Drinking Water Act primary requirements. Since passing secondary requirements is suggested but not required, some supplies may exceed the secondary limits. Exceedances are usually the minerals such as sodium, chloride, or sulfate. Iron and manganese may also exceed it in some locations. This varies on geography. If your water exceeds these and the taste of your product matters, you may want to consider extra treatment. In addition, since public supplies are disinfected, there is a very likely chance that this water will contain residual disinfectant, either residual chlorine or chloramine, and some of the disinfection byproducts. They will be present, but in compliance with the disinfection byproduct rule. Also, corrosion inhibitors, such as phosphate and alkalinity, may be added to the water so that it does not dissolve lead from pipe fittings. Think about Flint, Michigan, where to save money, the phosphate was not added, causing lead fittings to corrode. As we have mentioned previously, private supplies are usually groundwater. You will need to add disinfection or routinely test to make sure that bacteria are absent. As you know, water is a universal solvent and will always contain dissolved salts. Some of the ones mentioned here are included in the secondary Safe Drinking Water Act pollutant analysis. I always recommend a cation-anion balance because it gives you the full picture and provides you extra quality assurance. If the analysis does not balance, something is missing or one of the numbers is wrong. As a note, fluoride is usually always added to public supplies. The disinfection byproducts that we mentioned earlier are trihalomethanes such as chloroform and haloacetic acids. These form as organic matter from TOC, total organic carbon, reacts with chlorine during disinfection. Many facilities use chloramination to lower the trihalomethane and HAA concentrations. TOC is naturally occurring and present in almost all surface waters. It results from the breakdown and decay of vegetation in the watershed. Bromate can result in disinfection of water supplies that had a high bromide content. Usually this is water sources near the coast. Manganese is sometimes added during treatment to reduce the TOC prior to chlorination. Manganese and iron are also naturally occurring. As mentioned earlier, phosphate is added as a corrosion inhibitor. In private supplies, your biggest concern is always going to be the pathogens. You should monitor these often or disinfect. Even if you disinfect, you should still monitor often to demonstrate the effectiveness of the disinfection. E. coli, or fecal coliform, is your indicator organism for human or animal waste and potential for waterborne diseases. There are fairly simple presence-absence tests that you can do daily without too much investment. Keep in mind, compliance testing is very complicated due to regulations. I still recommend that you would fully characterize the dissolved mineral content of your supply. You will need this data to decide if further treatment is necessary and what kind of treatment that you should do. The dissolved constituents in water supplies is highly variable and very dependent upon the geography and the geology. Water has a tendency to dissolve certain elements from the surrounding rock. Surface activity can leach into surface and groundwater. Shown here is arsenic distributions nationwide. Not shown is this distribution is geologically controlled by the rock formations the water came from or contacted. In addition, higher concentrations of arsenic in the west are associated with influence of volcanic activity. As we have mentioned, all municipal or public water supplies have undergone some sort of treatment, usually by licensed operators. These facilities are heavily regulated by the EPA. The greater the population served, the more testing they must do. At minimum, source waters are disinfected, particulate and dissolved solids are precipitated and allowed to settle. Then the water is filtered, disinfectant is added again, and the water is pumped into the distribution system. Each facility has a quality control laboratory that does routine testing for bacteria and other contaminants depending upon the source. Each facility has online meters to verify that turbidity is low, the pH is just right, and residual chlorine is high enough to be within EPA minimum limits at the farthest point. At minimum, test your private well for total or fecal coliform. Install some type of disinfection, whether ozone, UV, or chlorination. If the source water contains contaminants not removed by a traditional treatment, a facility may also use some sort of advanced treatment. On a large scale, these are much more expensive than traditional treatment and may involve filtering through activated carbon, UV oxidation, and microfiltration. To summarize, public water supplies must comply with the Safe Drinking Water Act primary pollutant maximum contaminant levels and are distributed to your facility pathogen-free. They most likely will contain disinfectants and disinfection byproducts below the EPA regulatory limits. General water quality or cation-anion balance may vary seasonally depending on the abundance of water in the watershed. Chemicals are added to prevent corrosion. These chemicals will cause a scale to form instead. Eventually, you will see this buildup of scale. However, the rate is dependent on the TDS. Private supplies could contain pathogens. You can monitor them on your own with available kits. For compliance, however, you must use a certified laboratory. Larger aquifers with protected recharge zones will provide very dependable, long-term, consistent water. World Health Organization guidelines may be used as a basis to develop water quality standards. WHO lists some potential contaminants and explains why you should test for them. Generally, pathogens are the greatest risk because the effect is near immediate. Often, by the time you know there is a pathogen present, many people have already been exposed. Chronic contaminants are the chemicals that can have an impact on health after long-term exposure. Limits are based on toxicity and expected volumes relative to body mass that you may consume. Globally, water monitoring follows a similar pattern regardless of the country. A list of compounds to look for called targets is established. Standards including analytical methods and maximum contaminant levels are also established, and then legislation is written. A municipality provides the water to the public, and compliance of the municipality to the legislation standards and limits is enforced by a surveillance agency. In most countries around the world, legislation is written that establishes maximum contaminant levels for certain water uses, and any method capable of measuring below the maximum contaminant level is allowed. This differs in the United States. In the United States, maximum contaminant levels are established along with approved methods. Laboratories must become certified and can only use the EPA certified methods to monitor for compliance with federally regulated drinking water contaminants. On the federal level, you do not need to be certified or use approved methods for secondary or non-regulated analytes. However, most states and accreditation authorities will require you to use an EPA-approved method for secondary contaminants. An example of a target list is the EPA list of primary pollutants. This lists several metals such as arsenic, lead, selenium, mercury, and it lists organics such as chlorinated solvents and pesticides. Some of the secondary contaminants are iron, manganese, sulfate, and hardness. Eurofins Eaton routinely tests for these along with any state or World Health Organization specific additional analytes. We discussed the role of the EPA earlier. The U.S. EPA establishes primary, secondary pollutants and maximum contaminant levels. The U.S. EPA also establishes the test methods that must be used for compliance monitoring. You are not allowed to use other methods, nor can you modify an EPA one. State agencies may set standards that are more stringent than the EPA, such as require a lower maximum contaminant level. To measure lower may require a modification of a drinking water method. We are allowed to do this on a state-by-state basis. In addition, states have the authority to add and require monitoring for additional analytes that are not regulated at a federal level. In these cases, there may be no method forcing laboratories to develop their own. Since California has a tendency to add new analytes, Eurofins Eaton has been in many situations requiring development and validation of new methods. Eurofins Eaton has become known nationwide as a laboratory at the forefront of new method development, either for internal use or in collaboration with the US EPA. Water testing is a major component of the Food Safety Modernization Act. The Food and Drug Administration requires that growers begin sampling agricultural water to create a microbial water quality profile when they need to start complying with the Act. All growers have 2 to 4 years to complete sampling. How many samples are needed is not very clear. FDA is revisiting the water requirements outlined in the Produce Safety Rule. At present, the rule states that for surface waters, 20 samples collected over 2 to 4 years would be needed, then 5 samples every year following. For well water, it would be 4 samples, then 1 sample every year. They are working to simplify these standards. I do not know when the new standard will be published. Water should be tested for generic E. coli. There is no need to test for any other organism. There are different methods that laboratories use to assess generic E. coli, but the one FDA has set as a standard is EPA method 1603. The maximum holding time for this method is 6 hours. You must find a lab near you. Any water that touches the final harvestable produce, including spray, is called agricultural water. If the grower uses drip and it is working properly, this is not called agricultural water. However, if that same water source is used for spraying over or over irrigating, it is agricultural water. So what should a grower do now? If you're a grower who has been sampling for a third-party audit, you should continue to sample just using the same frequency and method that you have been using. Any grower who has not been sampling may want to begin sampling just to get an idea of their water quality. Eurofins is your full-service laboratory with plenty of support for the analysis of water. My particular laboratory, Eaton Analytical, consists of 2 locations and is certified in all 50 states for Safe Drinking Water Act compliance monitoring. We also routinely analyze bottled water from all over the world. A unique facet of Eurofins Eaton is that we are a specialty lab, meaning we do not take in wastewater or other highly contaminated samples. This is to ensure a concentrated effort on compliance to drinking water methods. The associated strict quality control assurance required and minimal chance of cross-contamination. If it is required to be tested in drinking water, most likely we do it. In addition, we specialize in participation in the EPA's unregulated contaminants monitoring rule and also lead the nation in testing for compounds of emerging concern. You can trust us for your drinking water testing needs. Thank you very much.
All right. So thank you, Ruby and William, for your presentations. We're going to move into a short Q&A session. We only have about 5 minutes. So everyone that's watching still, feel free to continue to submit your questions throughout the session, and the speakers will follow up with questions that they don't get to. Okay, for our first question, Ruby, this is for you. Are there any limits for microbes in compressed air?
So currently there are no limits through 8573. That part of the ISO 8573 is currently being revised, so it's possible that we will see some limits established there. But no, it's really hard to find anything specifically for compressed air in microorganisms.
Okay. Let's do another question. How do you suggest taking compressed air samples?
So basically, there's you know, a few different laboratories that specialize in this, and we have methods where we collect particles either with a membrane or with a laser particle counter. We can use that. Oil, you know, is collected either with a filter membrane for the oil aerosol. We use charcoal tubes to collect oil vapors that are then extracted and run through a gas chromatograph mass spectrometer. So, you know, each service company will have their unique ways of capturing samples. Basically, you've got to run air through it at a sufficient volume to be able to get to some of the lower limits. Water can be done with hygrometer, detector tubes, sensors, and it's not too complicated.
Okay, thank you. Here's another question. What is MCL for yeast and molds, conductivity / resistivity, and total plate count in water samples?
Can I get back to you on that?
Yes. So any questions that we don't answer during the session, speakers will follow up with you afterwards individually. I think that's all the time that we have today for our questions and for this webinar. I wanted to remind everyone that a recording of this webinar, along with a copy of the slides and Ruby's links, will be available to you within 3 business days, and this will come to you via email. Thank you, Ruby and William, for your expertise and your presentations, and thank you, everyone, for attending.
Thanks for the opportunity.
Thank you.